As we noticed when doing our earlier examples, it would be useful for us to develop some calculus to be used when studying parametric curves and parametric equations. Please download the handout. That's handout number 16 on calculus with parametric curves. You can find that on Nexus. So please download that and follow along. Well, before we get started, let's just recall that if you're given a curve C, so here's a curve C, and you want to know what the slope of the tangent line L to this curve at some point x naught, y naught is, so here's my curve C in this drawing, and we want to know what is the slope of the tangent line L to this curve at x naught, y naught. Well, that's just the instantaneous rate of change of y with respect to x evaluated at the point x naught, y naught. So the slope of the tangent line to our curve C at the point x naught, y naught is just the instantaneous rate of change of y with respect to x at the point x naught, y naught. In other words, it's dy dx evaluated at x naught, y naught. So what's the equation of this tangent line? Well, it's y minus our given y value, that's y naught, equal to m, our slope of this line, which as we said is dy dx evaluated at x naught, y naught, times x minus our given x coordinate x naught. What about the normal line to the curve at x naught, y naught? Well, what do we mean by the normal line? So the normal line at x naught, y naught is the line that passes through the point x naught, y naught, and that is perpendicular to the tangent line. Well, because n is supposed to be perpendicular to the tangent line, its slope is going to equal the negative reciprocal of the slope of our tangent line. So the normal line to C at the point x naught, y naught has slope equal to minus 1 over m, where m was the slope of the tangent line. And therefore, what is its equation? Well, the equation of this normal line, it's just going to be y minus our given point on the line, y coordinate of the given point on the line, which is y naught, equal to its slope, which as we said is minus 1 over m, times x minus our given x coordinate, which we said is x naught. One note to make, and this is stated on handout 16 that you'll have downloaded, is that we're always going to assume that our parametric equations are defined by what I have called nice functions. In other words, we're always going to assume that the functions f and g are differentiable, and we're going to assume that their derivatives, f prime of t and g prime of t, are also continuous. These conditions are always going to be satisfied for us in practice. So we're assuming always, without actually saying it, going forward, that our functions f of t and g of t, which are defining our parametric curve, are always going to be nice functions. So they're differentiable with continuous derivatives. Okay, here is our main result concerned with finding the slopes of tangent lines and normal lines to parametric curves. So we suppose that C is a parametric curve defined by these parametric equations here. Again, we're assuming f and g are differentiable with continuous derivatives. Well, we want to know what is the tangent line L sub t to a curve C at a point xy corresponding to the parameter t. All right, well, that, of course, is, as we just said, going to be given by dy dx, instantaneous rate of change of y with respect to x at the point xy. Now, because points on our parametric curve are going to be described in terms of values of our parameter t, we'd like to have a formula for the tangent line to our curve C at a point corresponding to a value t described in terms of that parameter t. So that's what this first statement does. So what is the slope of the tangent line L sub t to our parametric curve C corresponding to the point on our curve at t? Well, I've denoted that by m sub t to indicate that this is corresponding to the point on our curve at the parameter t. That is equal to dy dx, certainly. And what's that going to equal? That's going to equal g prime of t over f prime of t, where y, remember, was g of t and x was f of t. So we have g prime of t, derivative of y with respect to t, divided by f prime of t. What's f prime of t? That's the derivative of x with respect to t. So in Leibniz notation, m sub t, the slope of the tangent line to our parametric curve at t, it's going to be dy dx evaluated at this point. That's going to be dy dt over dx dt. Of course, this is assuming that this denominator f prime of t, which is dx dt, is not equal to 0. Now we should take a minute to see how nice the Leibniz notation is, and this is going to help you remember this formula. So what is dy dx at t? It's just dy dt over dx dt. So if these dt's and dx's actually were numbers, you would have this natural cancellation of these dt's. So if dy, dt, dx, and dt actually were numbers, they're not, they're just symbols, but the symbolism works extremely well, is my point here. If they were numbers, well, this would look like dy dt times dt over dx. Those dt's would cancel, and you'd be left with dy dx. So what is dy dx? It's just dy dt over dx dt. I think the Leibniz notation really helps us remember that. Now, on to the normal line. Well, the normal line to see at the point xy corresponding to the parameter t, what is its slope? Well, we know that the normal line has slope equal to the negative reciprocal of the slope of the tangent line. So its slope is minus 1 over m sub t, where m sub t is the slope of the tangent line at t. Well, what's that equal to? Well, if m sub t is g prime of t over f prime of t, minus 1 over mt is, well, we just take the negative reciprocal of this quantity here, and we have minus f prime of t over g prime of t, which is the negative of dx dt over dy dt. Again, of course, assuming that this denominator is non-zero. All right, I want to provide a sketch of the proof of part A. Part B was immediate from part A. So we suppose that C is our parametric curve described by these parametric equations here. And remember, we're assuming that f and g are nice functions, so they're differentiable with continuous derivatives. So we're going to take a fixed point x naught, y naught on our curve and say that it corresponds to the parameter t naught. So x naught is f of t naught and y naught is g of t naught. So we've fixed a point on our curve, and we're going to assume that f prime of t naught is not 0. So what do we want to do? Well, we want to show that the slope of the tangent line to our curve C at the point x naught, y naught, which we know is going to be dy dx evaluated at x naught, y naught equals what the proposition said it equals. We want to show that it equals g prime of t naught over f prime of t naught. Well, in other words, it equals g prime of t naught, that's dy dt at t naught, divided by f prime of t naught, that's dx dt, evaluated at t naught. So that's what we're trying to show. All right, well, let's first, and as we said, we want f prime of t naught to be not 0, otherwise this isn't going to make sense. All right, so to begin, and I'm going to not write all the details here. There are more details that you can find in handout 16. We're going to let z equal this derivative function of f. So x is f of t, and I'm letting z equal the derivative function. That's f prime of t. Now, because f prime of t naught is not 0, either f prime of t naught is bigger than 0 or it's going to be less than 0. Let's suppose that f prime of t naught is bigger than 0. The case where f prime of t naught is less than 0 is similar. So here I've drawn z at t naught so that it's less than 0. So z equal to f prime of t naught is supposed to be bigger than 0. Now, remember, we're assuming that f prime of t, in other words, z, is continuous. So if z is continuous, in particular, it's continuous at t naught, and in fact, it's continuous everywhere, and f prime of t naught is bigger than 0, what can we say? Well, if z equal to f prime of t naught is going to be less than 0 anywhere, well, say maybe over here it's less than 0, because it's continuous, its graph has to come in one piece, we can see that it's still going to have to be positive on an interval containing t naught. So it's might eventually become negative, but nonetheless, because of continuity, we can say that there definitely is going to be an interval AB that contains t naught where z equal to f prime of t is bigger than 0. All right, I've written that here. We know that z equal to f prime of t must be bigger than 0 on some interval AB containing t naught. But what do we know? If a function's derivative is positive, we know that the function itself is increasing. So x equal to f of t, our x-coordinate must always be increasing on this interval AB containing t naught. Well, let's see what that means. All right, so I'm going to give a sketch of our parametric curve, which was described by these parametric equations here on the interval AB. So at x naught, y naught, remember, was a point on our parametric curve corresponding to t equal to t naught. Suppose that at a, that's this a right here, we have this point here on our parametric curve, and this is our point on the parametric curve corresponding to t equal to b. Now, as we just said, we have that x, our x-coordinate, x equal to f of t, is increasing everywhere on the interval a, b. So as t increases from a to b, passing through the value t equal to t naught, our x-coordinate everywhere has to increase. Well, this is our x-coordinate right here. So our x-coordinate must increase as t increases from a to b. In other words, as we follow along the curve determined by these parametric equations, we must actually move from left to right to ensure that our x-coordinate is increasing. All right, so let's draw that. I have to do something like this. right? So between t equal to a and t equals b, our x-coordinate must increase. What would happen if our x-coordinate did not increase? Well, we would eventually start doubling back. So if I move in this direction, as I move from left to right, x-coordinate is increasing, and as soon as I start moving from right to left, the x-coordinate decreases. X-coordinate increases, x-coordinate decreases. Well, what does this mean in particular? This means that this portion of our curve, our parametric curve here, must actually be the graph of a function y equal to f of x. Why is that? Well, if our x-coordinate were allowed to increase for a while and then decrease for a while, say suppose we did something like this. I'm going to erase this in a moment. Starting at t equals a, I move in this direction and then I start doubling back. So that's a picture of x-coordinate increasing and then decreasing, increasing, decreasing. We could see that for some values of x, I would have two corresponding y values, and this portion of our parametric curve would not be the graph of a function y equals f of x. But in this case, this portion of our parametric curve is the graph of a function y equals f of x, because it's not possible for us to have two y values corresponding to any one x value. All right, to summarize, the portion of our parametric curve, C, so I'll label that as our parametric curve, C, from corresponding to values of t between a and b, actually is the graph of some function y equal to f of x, and elsewhere for other values of t, we don't know what it looks like. I'm just drawing whatever here. It's not actually relevant. All right, so as we said, what we have is that this portion of our curve here looks like a y equal to capital F of x, where x is described as f of t, and our y here, y is described as g of t, and this is for t in the interval ab. What do we want to show? Well, we want to show that the slope of our tangent line here, looks like it might be horizontal, but that's not relevant. This is just happens to be the way I drew it here. We want to show that the slope of our tangent line to C at the point x naught, y naught, which is going to be equal to, given that this is part of a y equal to f of x, which is going to equal then capital F prime of x naught, the derivative of capital F evaluated at x naught, we want to show that that is equal to g prime of t naught over little f prime of t naught. In other words, we want to show that it equals dy dt at t naught, that's g prime of t naught, divided by dx dt at t naught, that's little f prime of t naught. If we can now derive this statement here, what we have in the yellow, we'll be done. So let's see that we can, in fact, derive this statement. So we have y is f of x, where x is f of t, and y is g of t for t in ab. So rewriting this y equals f of x, what do we have? This y is g of t. So on the left side, I've written g of t. And the x here is little f of t. So capital F of x becomes capital F of little f of t for t in AB. All right, well, now we can differentiate both sides and we'll get the same thing. Differentiating the left-hand side, we have g prime of t. And if we differentiate the right-hand side using the chain rule, we'll get derivative of the outer function, that's capital F prime, evaluated at the inner function, that's little f of t, and then differentiating the inner function, we have little f prime of t for t in AB. So this holds for any t in AB, and so, in particular, it holds at t naught, the point we started with. So we have g prime of t naught is equal to capital F prime of little f of t naught times little f prime of t naught. But remember, our original point on our curve, x naught, y naught, was the point corresponding to t equal to t naught. So what is this little f of t naught? Little f of t naught, that was our point x naught. So rewriting this, just replacing this little f of t naught by x naught, we have what I've written here. G prime of t naught, that's the same as before, equals capital F prime of x naught times little f prime of t naught. That's the same as before. Now, solve for capital F prime. There should be a prime there. Solving for capital F prime of x naught, we have capital F prime of x naught is g prime of t naught divided by little f prime of t naught. All right? Well, that's what we wanted to show. We wanted to show that capital F prime of x naught, the slope of the tangent line to our curve at x naught, was g prime of t naught over f prime of t naught, and that is what we've done. And so we've established the statement we wanted to establish. Done. Remember, all these details are also written in handout 16. As you know, we're always particularly interested in knowing when our curves have horizontal tangent lines or vertical tangent lines. And our last proposition allows us to determine exactly when a parametric curve is going to have a horizontal tangent line or a vertical tangent line. Well, when is our parametric curve going to have a horizontal tangent line? Well, that's going to be when dy dx is equal to 0. Well, what is dy dx? Well, we know that dy dx, the slope of our tangent line, is given by dy dt over dx dt. So dy dt is equal to g prime of t, and dx dt is f prime of t. So if we're looking for a horizontal tangent line, we're looking for when m sub t, the slope of our tangent line, g prime of t over f prime of t, is 0. When is that going to be? Well, that's going to happen when does this quotient get to be 0? Well, when the numerator is 0 and the denominator is not 0. So we can say that we'll have a horizontal tangent line when dy dt, which is to say g prime of t, is equal to 0, provided that our denominator here, f prime of t, is not 0. Okay, when are we going to have a vertical tangent line? Well, we're going to have a vertical tangent line, you might notice, when the normal line, which is perpendicular to our tangent line, is horizontal. Okay, so we're looking for when the normal line is horizontal. Well, what's the slope of the normal line? The slope of the normal line is, as we said in the above proposition, what we call 10.2.a, you can look above, it has slope minus f prime of t over g prime of t. That's the negative of dx dt over dy dt. When is this normal line horizontal? In other words, when is this slope of the normal line equal to 0? Well, that's going to happen when the numerator is 0 and the denominator is not 0. So, in other words, when f prime of t is 0 and g prime of t is not 0, the normal line will be horizontal, and therefore the tangent line is going to be vertical. So to summarize, C is going to have a vertical tangent line when dx dt equal to f prime of t, this numerator here is 0, and the denominator here is not 0. Of course, we don't really need to remember this statement here so much as we need to remember the proposition up above, which told us the general formula for the slope of the tangent line to our curve at t and the slope of the normal line to our curve at t, and then we can just derive that corollary using exactly the same logic that I just outlined. Each time we need to apply it. In other words, each time we're looking for a horizontal tangent line to our parametric curve or a vertical tangent line to our parametric curve. All right, well, that was a bit of a theoretical sort of derivation there. This year, I'm not going to ask you to provide these proofs on the final exam, but I think it's worth your time to try to understand our derivation that we gave of proposition 10.2.a part A. So do that, and if you have any questions, you're welcome to ask me. In our next video lecture, I'll give some examples where we will in fact use this proposition.